So change in the kinetic energy can be expressed in like that. So if I multiply dt, then it becomes total derivative of gamma v squared and this. The change in kinetic energy is m0 minus m0. I can put 1/2 and dv squared gamma. Right? So if I take the integral, this is just gamma v squared v and v equals 0. At v equals 0 it is 1 and this is 0. So this gives m0 gamma v squared, right? And second term is minus m0 gamma is this, and let me put c squared in the denominator and multiply c squared here. And this is dx over square root 1 minus x. And this is minus d 1 minus x 1 minus x minus square root y dy, right? What is the answer? Here, y equals 1 minus. If I take the square root of root x derivative x 1/2 at derivative, therefore am I right? Right? So minus 2, where is minus? Okay, minus 1. Minus 2 makes this one to be m0 c squared. Minus becomes plus and 2 disappear, and square root of y. Square root of y. Y is 1 minus c squared v squared. Alright? So what is that? Let me factor this 1 minus c squared v squared in the denominator, that is gamma. And because of this, it becomes plus m0 c squared 1 minus c squared v squared. And this guy and this guy is exactly the same, they cancel. The answer is mc squared, m0 c squared. That is m0 gamma c squared. Aha. Aha. What was that? This is, if I put this one c in the denominator, it becomes m0c squared. However, I think I missed something. Because here, this is the integral and this is the final value, and so I must subtract this one by initial value where v equals 0. So there should be 1, right? So here minus m0 c squared is missing, minus m0 c squared. This means that gamma m0 c squared, which is zeroth component multiplied by speed of light, is kinetic energy change plus m0 c squared. Okay, so p0c is like that, and p0 for gamma m0c, this one is interpreted to be kinetic energy plus some energy that does not disappear even if the particle is at rest. If the particle is at rest, it is not moving and the kinetic energy is 0. So m0c squared is assumed to be some energy that is intrinsic to any particle with mass m0, which is the rest mass. Okay. Next step, we'd like to study what's going on with the transformation of derivatives. We have x spatial vector, and x vector squared is a scalar, and force is a vector, and sometimes force is expressed in terms of minus gradient of potential energy. And potential energy was assumed to be scalar. We remember this is a force. Force is mass times acceleration. Acceleration is time derivative of velocity, and velocity is the time derivative of position vector. Okay, this is a vector, and in classical mechanics, time is a scalar, so this is a vector. This is scalar, so acceleration is scalar, vector. Acceleration is vector, mass is a scalar, so vector, force is a vector. But from this, we can see that gradient, so derivative of a scalar, transforms like a vector. So let's see if it is really true. On the rotation, x prime I equal r I j x j. Let us take the derivative with respect to xj. Ij. j equals I'm interested in the transformation of derivative. So what I want to know, x I prime is, what I have to know is this guy transforms like r, I, j. Am I right? If it is right, if this guy is a vector, it should transform exactly the same as x prime I, rij. So if this is true, this is, I don't know. Okay, how can I express this? I can make use of chain rule. X prime derivative can be k prime I am I right? Our problem is that this guy is different from this. What should I do? What should I do? If I want to find the unprimed in the numerator, what I have to know is the other part. So this is x prime equals r x, something like that. If I multiply r transpose is actually inverse. We remember. Let us put indices. No, I. But what I'd like to know is k and I, so it's good to use k. K and I. Okay? So if I take the derivative with respect to I prime, that is transpose, so R, I, K. So I substitute this guy here. Aha. This one transforms like x prime I equals R, I, K, x, K. So that's the reason why derivative gradient is transforming just like the vector. So what happens to the four vector case? In that sense, this guy. Sum over I. This is a transforms like a scalar. Okay. Let us copy a similar way. X prime mu lambda mu nu x nu. Right? Then, if I take the derivative x prime mu x nu, so lambda mu nu. Okay? So, what I'd like to know is and what is that? Again, we have to find the reverse form. How can I find the reverse form? We remember inverse relation. If you have forgotten, then let us derive one more time, or just copy previous result. Copy previous result. What was that? If you don't remember, it's better to write it immediately. Here, similar shape. Let me use alpha. New x new. New x new. So let me use this one, alpha alpha. And multiply this guy, both sides, mu beta, and I have this and this. This becomes g alpha beta x alpha. That means x beta is mu beta x prime mu. Okay, so this is beta in the downstairs. I can move it up. If I take the derivative with respect to beta, this guy, all right, here, mu is the same. Let me change this one as nu. So this is lambda mu nu okay. So what we find here, if I take the derivative with respect to the contravariant variable, it becomes covariant. The reason is that x times something is mu a mu something. If I take the derivative with respect to lower index, then the result is upper index. Okay? So, another way of writing is this guy resembles Let us copy. If I rewrite this one as a simple expression, round, this is a 4 vector, but derivative with respect to a covariant one is contravariant one. Contravariant one. Okay? This guy behaves not like a covariant one, but like a contravariant one. So this is contravariant. This guy transforms in the same way. But this is the big difference between this Minkowski space and Euclidean space. As a result, what happens to this kind of form? Zero is always the same. And space okay. And this guy is what? Minus gradient. Anyway, this guy is invariant on the Lorentz transformation. It transforms just like a scalar. Finally, we remember that the components of electric field and magnetic field satisfy what equation? Wave equation. And this wave equation was not invariant on the Galilean transformation. However, we have found that this expression is invariant of Lorentz transformation. That's it for today.